Hello, this is Bryant Myers, and welcome to another episode of Debunking Flat Earth. Tonight we got a really good one here. We're going to go through all of the main flat Earth objections to gravity, especially at the cosmological scale. And I'm going to go over general relativity and all the proof because it's something I didn't really have time for in my presentation. So as before, let's just start with a little soundbite from Austin, then we'll come back and talk about it.
And it'd be different if you had a new theory, but you still use Einstein's theory of relativity, even though it's drastically incomplete. It's been debunked. It doesn't work on the quantum or cosmological scale. It's incompatible with quantum. It doesn't work at all, and you just keep it. But it'd have to work on all scales if it was real. It doesn't make accurate predictions, though.
Well, again, where's your model that does that?
Electrostatics.
Okay, so that was Austin basically saying that general relativity is not accurate. It's not compatible with quantum mechanics. It's debunked, all these things, which are all false, by the way. No credible scientist will agree with Austin. And then he ends with, well, what is accurate? And he says the electrostatics. It's kind of funny that he can't even get 9.8 meters per second squared outputted from his model. And yet he's trying to debunk one of the most accurate models that the human mind has ever come up with in general relativity. So let's kind of go through Einstein's gravity here. And now, as accurate as Newton's laws are, there are definitely some problems when we start getting to really fast objects and strong gravitational fields. So now, interestingly, Newton's laws were good enough to predict that the planet Neptune, with the perturbations in the orbit of Uranus, we were able to know that there's a planet, and Newton's laws are so accurate that they can predict the planet should be here at this particular time and day, and sure enough, they get the telescopes out and they say, oh, look, there's Neptune. So we use Newton. This is a great vindication of Newton's laws, that we actually were able to use Newton's laws to discover Neptune, the planet. Now, really interestingly, with Mercury, there were also perturbations. And they actually said, okay, well, we discovered Neptune from perturbations. Maybe there's another planet around Mercury. They actually call it Vulcan, but they couldn't find there was no planet there. And we'll see here in a minute that general relativity explained what was going on. So general relativity, it's like 10 field equations. I mean, and they're tensor equations, so they're very, I'm not going to pretend to be any expert in general relativity. I mean, I understand the principles behind it, but these are like graduate level classes, and you really have to go deep into like a PhD in physics to really get a handle on solving general relativity problems. Okay, so this is something I kind of want to draw your attention to. I want to bring this point home here, is that, I've heard Whitsitt say this, that, relativity debunked Newton, and it didn't. Actually, Newton's laws, and I kind of mentioned this during the debate too, Newton's laws of gravity they're right here within Einstein's field equations when you get a solution in potential form. And then you have this new term here. And this is it's like a correction factor. So this is very, very, very small, almost zero in most everyday situations. It's so ridiculously small. The only time this term gets large is when you have a large mass and you have relatively large, speeds as far as, rotational speeds. And so this will definitely, so you can see that this will affect the rotation speed. This is the mass. This is exactly what happened with Mercury and the Sun. You have a very large mass, the Sun, and you had Mercury very, very close to it. So this gives rise to a situation where we have to use Einstein's general relativity. And it predicted the perihelion precession of Mercury with incredible accuracy. And again, we didn't know why Mercury had these perturbations, but with relativity, we could solve the field equations and see this orbital precession of Mercury around the Sun. And again, because the gravitational field is strong enough that general relativity had to be invoked. But pretty much for the rest of the solar system and here on Earth, we never really need to use general relativity. Another great vindication of general relativity was gravitational lensing. And we can see gravitational lensing all over the universe with magnitudes that align with the cumulative masses the light is bending around. Incredibly accurate. And Sir Arthur Eddington was the first to really use this to vindicate relativity, and it really was one of the first tests where people were like, yes. Because again, there's a lot of skepticism around relativity. But when this test came along, that really put an end to the skepticism, at least a lot of it. Because Einstein postulated that the path of light could be influenced as it passed by the gravitational field of a large body. And this gravitational lens would deflect the light by a very specific amount. And so after mapping the exact relative positions of stars, these positions were compared to the apparent positions during an eclipse. And that's what Sir Arthur Eddington did, is that he measured the actual positions of these stars during this eclipse and could see that they were bent from where they should have been by exactly the amount that relativity predicted. Again, incredible validation for the theory. Now, something that Whitson and some of these others don't get is that our GPS system literally relies on relativity. In fact, it's really interesting because you have both special and general relativity both being vindicated by satellites, GPS systems. So it gives rise to the first is a gravitational effect. So because the clocks on the satellites are at a higher altitude, the gravitational field is weaker. So the clocks will speed up relative to the Earth. But on the other hand, the speed of the orbits around the satellites is faster. And through special relativity, we know that the time will slow down by going faster. It's basically 45 microseconds from the gravity, and you subtract -7 microseconds from the speed due to time dilation, and you get only 38 microseconds a day error on the clocks, which doesn't sound like a lot, but because these GPS systems are moving so fast and they're covering such a large planet in such big distances, this can give rise to an 11-kilometer error if you're not correcting for time dilation and time speeding up and slowing down, in both cases. GPS is literally proof that relativity, both special and general, that relativity works. Now, I kind of like this Pound-Rebka experiment because it actually meets the criteria of flat earthers that you can manipulate the independent variable to create the cause of the dependent variable, which, by the way, is not the scientific method. That they're just saying it's got to be this way, but flat earthers make a lot of demands that scientists themselves never make. But the interesting thing is we can actually shine like a gamma ray from a tall building, and we can notice that the light actually falls in the sense that it doesn't speed up. Light's always the same speed, but the energy does increase by falling to the Earth because of the gravitational field. And this will actually increase the frequency of the light. And it's kind of interesting that you're increasing frequency. So the energy is increasing the light, but it's not kinetic energy. It's not like normally when you drop a ball, the kinetic energy is the increased energy. Here it's E equals hv, and it's the energy of the photon that increases, but it's in perfect alignment with general relativity. Now, here's another, of course, to me, this is one of the best vindications is the LIGO detection of gravity waves in 2016. Now, flat earthers tried to debunk this, and again, in my first debate, they said, oh, those numbers were faked and whatever. And there was a Danish physicist that was basically making that claim. But again, this is one physicist out of pretty much the whole community of physicists, and his data was not accepted by anyone. So, and even if hypothetically, okay, the first measurements were something was wrong, which it wasn't, but they've detected gravity waves many times since then. And the example I want to go over, to me, is the best proof of all of these experiments, because what it did was they used the LIGO in the United States and the Virgo in Europe to extract gravitational wave signals along with light signals at the same time. And this is really cool. There was gravity waves from a binary neutron star system. And this event also released gamma rays, a burst of short gamma rays. And so the conclusion, which is really cool, is that the gravity waves and the gamma rays came in at about the same time. Again, the time differences were absolutely predicted. And it showed amazing confirmation that these gravity waves detected from this binary neutron star system were absolutely the gravity waves from this system, because they got the gamma ray burst right after it. I mean, this was the first time, by the way, where they were able to detect light from a distant system like this, or electromagnetic waves, and gravity waves at the same time. What do you say to that, flat earthers? Try to talk yourselves out of that one. That is incredible validation. And again, the LIGO numbers that they get are like to many decimal places confirm Einstein's general relativity. I mean, it's not just 1 or 2 decimal places. I mean, general relativity, based on the LIGO experiments or the LIGO detection of gravity waves, is some of the most accurate science that's ever been done, along with, quantum electrodynamics is incredibly accurate as well. But it's not been debunked, Austin. You say that relativity's been debunked. No, it hasn't. Not even Newton's laws have been debunked because you don't understand how science works. You don't understand what a scientific law is, and you don't understand what a scientific theory is. Even though you've been told repeatedly over and over and over again, and I've heard other debates you've done, you just don't seem to listen. And here's the thing, here's my challenge to Austin. Okay, Austin, if you're so smart and you think that this is not a real study, well, read this paper yourself. I would like to see your analysis of where this paper went wrong and what is not accurate about it. And and here's the thing. So Austin somehow is smarter than these like 200 scientists that were part of this experiment. And these are some of the smartest people in the world too. And if you've listened to some of Austin's debates, I mean, I'm not saying he's not, he's got some intelligence, but, well, I'm trying to be nice here. But you're trying to tell me, Austin, that you know more than all of these scientists that were a part of this incredibly accurate experiment, that for the first time ever, we were able to detect gravity waves and light from the same system at a distant location, and they predicted what Einstein would say almost exactly. I mean, and look, just soak this in, everyone. Look at all these people. So this is what's kind of hilarious for me, is that flat earthers think they're so much smarter than everybody else. And they're so much smarter than the thousands of the smartest people in the world that are discovering and working with these things. It's seriously laughable when I hear Austin say relativity's been debunked. Not one of these people in this study would agree with Austin. Not one of them. I mean, Austin does have a point. With dark matter, dark energy, the vacuum catastrophe problem, there's some problems and unknown answers in our current model. But here's another reason why relativity is not debunked, is scientists will put general relativity with the Big Bang cosmological model, meaning we don't just use general relativity. We use the Big Bang cosmological model, which is a model that's incredibly well substantiated by empirical evidence, a lot of evidence. And there's still some unsolved mysteries, no doubt, but we have learned so much about the universe we live in. It's, first it started with the Kolbe microwave background radiation, then Wilkinson, then now it's the Planck system, which is giving much, much more accurate data. And the recession velocities of galaxies suggest a particular age of the universe, and the detection of the microwave background radiation corroborates this age. So there are some very good validations to this model. There's been just tremendous work since the early 90s on advancing our cosmological Big Bang model. And no, contrary to what some flat earthers say, the cosmic microwave background radiation does not corroborate the Earth being at the center of the universe. And you can just Google it and see for yourself. I'm not even going to get into that. It's just so laughable. And this is the thing that's kind of still a mystery. 68% of the energy matter density in the universe is dark energy, roughly, based on this current model, what we have. 27% dark matter, and only 5% is the matter that we all know. So yes, there are definitely some mysteries. In the standard Big Bang cosmology, there's a few things that it's really helping us to see. So again, above and beyond just general relativity, even though general relativity is really a big part of this. But it's guided by a lot more research based on observation of distant galaxies and rotations, all kinds of things. And so this is tremendous amount of labor has gone into creating this model. But again, by the smartest people in the world. And it kind of gives us the large scale structure of the distribution of galaxies. It showed us that the universe is expanding at an increasing rate. The model actually assumes that general relativity is the correct theory of gravity. This is the thing. I mean, again, why it's just so laughable, Austin saying that relativity has been debunked. I mean, it is the foundation or the cornerstone of our current model of Big Bang cosmology. Okay, so now I want to look at dark matter a little bit, and I want to just play another soundbite from Austin, because he seems to think he's like the expert on dark matter. But let's hear what he has to say.
I understand in 33 discovered that the galaxies only had 3% of the mass, and then it was ignored for decades, and now it's called dark matter. The idea, dark matter is the idea. You asked me how it works. I'm going to tell you how it works. It's the idea that it doesn't interact with the electromagnetic spectrum, and it's assumed to be material, but it's undefined. We don't know. It's a mathematical discrepancy with what relativity predicts. No one peer-reviewed dark matter. No one knows what it is. It's not even defined yet.
So what I kind of find funny about that is that Austin goes on to explain what he thinks dark matter is. And then he says it can't be defined yet. So it kind of contradicts himself there. So dark matter is there. It doesn't come from any theory that we have yet. But we can observe it. We can see its effects. And we know there's more gravitational effect than general relativity in our models can account for. So dark matter is a placeholder for something we just can't put our fingers on at the moment. It doesn't mean our theories are wrong. It just means that they're not totally complete yet. But we can still use these observations to make our models in our Big Bang cosmology work wonderfully. Just because we don't know the cause of dark matter doesn't mean that we can't use what we observe to make predictions. This is what Austin doesn't seem to get. You know, Newton himself didn't know the cause of gravity, but his equations worked just fine. And also we know this is a gravitational effect. So when Austin says everything is electrostatic, it doesn't apply. And he tries I've heard him before try to explain dark matter on other interviews with this kind of his ether model, but it's a gravitational effect. It's well known that it's a gravitational effect. And so that means that matter, it's still a mass attracting mass in a sense. It's just that this mass is kind of an unknown. We don't know really what it is yet. But we do know it's gravitational. And we can't see it, so we call it dark. Now, here's the thing. You know, saying that we don't understand dark matter at all, and Austin brought this up during the debate towards the end, and he just doesn't know what he's talking about. I mean, if you really want to understand dark matter, you got to look at some of these research studies. And so I just want to give you a little sample here what they look like. And again, Austin doesn't have a training in astrophysics, so for him to sound like he's some kind of authority on dark matter is just laughable. And again, if you can't follow what these studies are saying, then don't criticize it because you don't know what you're talking about. Again, and there's just hundreds of studies like this is what I'm trying to tell him. It's like, Austin, there are hundreds of studies on dark matter. Maybe we don't know the cause of it, what causes it, or where it came from, but through our observations, we do know its behavior very well, actually. And again, flat earthers just don't understand scientific laws and theories and how science works. Now, I just want to give one example of dark matter in the solar system, just to drive this point home, that our current model of general relativity in Newtonian mechanics works just great. This is a very top-level astrophysicist that did this little calculation, and he assumed the known density of dark matter within our galaxy, and he kind of, if you spread that dark matter density throughout our solar system, you can actually calculate how much mass that would be and how much an effect it would be on the orbits of the planets. And it turns out, when you do the calculations and you use what's called Birkhoff's theorem, which is kind of a Gauss's law equivalent to gravity, basically it's kind of the enclosed sphere. So if you have a particular orbit like, say, Mars, all the gravitational effects are coming within that closed orbital, you could say sphere or orbital, if you kind of draw it out into a sphere of sorts. And when you do these calculations, and you can do them for all the planets, you come to a range of 10 to the 13 to 10 to the 17 kilograms from the inner planets are going to have less, obviously, because they're smaller orbits, right? So they'll have smaller amounts of dark matter inside their orbits. Where Neptune will have the greatest amount of dark matter, which is 10 to the 17. But here's the thing. 10 to the 17 kilograms is literally the mass of an average size asteroid. It's not that much. Now, that's still a lot of mass, but when you compare it to the Earth, that's 6 times 10 to the 24th kilograms. Okay, that's 10 million times more mass than how much. So meaning the Earth has 10 million times more mass than all of the dark matter that is within Neptune's orbit based on this calculation. And as far as where we're at in the orbit, it's even much less. So you can see, this is why I want to put this little. Again, we got another correction here, and I did this myself. I don't pretend to be able to work with the computations of dark matter. It's a very complex subject, but we certainly, within science, it is known very well, even if the cause is not known. So I talked about before that here we have Newton's laws. So Newton's laws work. They're within general relativity. And we have to use a correction factor for, say, the perihelion of Mercury. But now, maybe a newer, better theory that will, general relativity is going to have to be a special case. We know it works. It's just that there's probably a newer and better theory, perhaps a quantum theory of gravity, who knows, that will now incorporate the dark matter, and it will show where that comes from, which we don't have it yet. But this dark matter correction is going to be so ridiculously small that it's not going to affect within our inertial frame of reference here on Earth and our solar system. It's not going to affect it at all. The dark matter comes into play in the rotation of galaxies at the large scale, and within galactic cluster formations, and within just huge. These are just ridiculously huge scales where dark matter starts to play a more dominant role. It doesn't play a role in our inertial frame here in our solar system. And again, flat earthers just, and I know this talk is a little complex or technical, but I just wanted to get it out there just for those people that love science, and hopefully some people that are researching flat earth that are on the fence, hopefully you can get an excitement for real science. I mean, to me, it's so much more interesting, so much more exciting than all this flat earth baloney. It's just, I mean, real science is just so much more interesting than all this made up science of the flat earth. Okay, last thing I want to talk about, because this is kind of going a little bit long today, is that flat earthers love to bring up Michio Kaku and his little quote, 10 to the 120th power. So what this quote deals with is the vacuum catastrophe, which is the mismatch between Einstein's general relativity and quantum mechanics, or quantum field theory. And it comes from the fact that within quantum electrodynamics, because here's the problem, and I learned this from my mentor at Georgia Tech, Dr. David Finkelstein, who didn't think that these numbers were accurate at all. And of course, string theory and loop quantum gravity doesn't have this problem. However, they haven't been proven yet. So we still just have to work with our standard model and these renormalization issues. And it's because of these infinities that arise when you treat particles as point particles. And within string theory, they're not points anymore. They're now vibrating strings. So these infinities go away. And it's just that string theory doesn't have the experimental validation yet. So we're still kind of stuck with the standard model, but it's incredibly accurate within its domain. I mean, it's impeccably accurate to like 8 decimal places. Quantum electrodynamics is really, I think, one of our most, if not the most accurate theory we have based on just its precision. If you go to Wikipedia, there is an article on the vacuum catastrophe, and they actually list some good studies that show solutions to this catastrophe. And when you model it in certain ways, it goes away. Okay, so just to kind of conclude here, I just want to say why the problems of Newtonian gravity and general relativity and why they're not a problem. That is, why the problems are not a problem. So we think classical mechanics is correct, even though both general relativity and quantum mechanics proved it wrong. We use classical mechanics every day in a variety of disciplines, including engineering and architecture, and we do so very successfully. Our machines work, our buildings stand. Why? Because the old theories were not proven blatantly wrong. What was demonstrated are their limits of applicability. In everyday scenarios involving non-relativistic speeds and gravitational fields that are not akin to black holes, Newtonian mechanics gives accurate answers. There's no need to account for post-Newtonian corrections. In everyday scenarios that do not involve individual atoms or elementary particles or fast speeds and strong gravity, classical mechanics works just fine. There's no need to apply quantum corrections. There's no need to use general relativity. It would be a waste of effort. This doesn't mean that we don't know what we're doing. It means that we understand exactly how good or bad these theories are, which means we know exactly what we are doing, even if we don't have all the answers at the cosmic or microscopic scales. General relativity and quantum field theory yield accurate answers, very accurate answers, tested through numerous high-precision experiments. So these theories, these cosmological theories are on the cutting edge of science. And there's going to be always unknowns on the cutting edge. But what we have, and just look at the world around you, look at the technology, look at the progress, the innovation. I mean, it was kind of laughable during the debate that Austin actually, he doubled down on it. He was like, I said, see, what you're telling me is the science of the 1800s is better than the science of today? And he said, yes. I mean, I couldn't believe it. And so it's because these flat earthers are stuck in their ether in this old science. I mean, I just really couldn't believe it that he was like, yeah, he really doubled down on that our science is not as good now as it was in the 1800s when we had ether. So anyway, I hope you enjoyed this video. It's a lot of information. I just want to give a little announcement. MC Toon and I are going to do a little funeral service for incoherent dielectric acceleration because I created the black swan. It's just a little whiteboard that absolutely kills dead incoherent dielectric acceleration. And I'll just conclude this by saying that it's, to me, it's the epitome of irony that Austin is trying to say that all these theories we have are debunked when they work so perfectly. Yet his theory, he can't even output 9.8 meters per second squared. I mean, again, I just hope people that are on the fence are just really listening to him and some of the nonsense that he's saying, all the contradictions, because their model just doesn't work. Our models aren't perfect, but they work impeccably. And again, technology and engineering are living proof that what we have as our scientific theories and our scientific laws work wonderfully. I mean, I love the world. We're living in a wonderful time right now with just great innovations and technologies. And we have science to thank for that. So I thank you for watching. Please do like and subscribe to my channel. I got many more coming. And I hope you have a really great night.